It's Paul again, and we're ready to go with the mystery of complex numbers. This is not a topic that's covered at length in the textbook, but it's going to turn out to be very useful when we look into sort of differential equations that are very important in physics. I'm assuming that you've looked through the page of the executive summary that contains subsections 1.6 through 1.8, and perhaps that you have listened to Kate's lecture preview on this subject. I apologize for the Westminster chimes in the background. This is not being done in a recording studio. It's being done in my basement office, and I just love the clock. Let's get started. Let's include vector library, but let's change the name to the correct one. And look at complex numbers. Turns out there are three ways to make a complex number in R. You can specify the real and imaginary parts, and you get 4 plus 3i. Or if you're feeling lazy, you can specify the real and imaginary parts. But because R likes to make everything a vector, you have to start with a 1 to show that there's only one complex number in this vector. Or you can specify the modulus and argument of the complex number, which are just like the length and angle of the associated vector. Now I'm going to do the same thing with vectors. Let's start with a plot so that we can look at this and show the imaginary part plotted vertically, the real part plotted horizontally. There's the complex number whose real part is 4 and whose imaginary part is 3. Let's try adding some complex numbers. Z1 and Z2 are two complex numbers. V1 and V2 are a pair of vectors that look surprisingly similar. And sure enough, if we plot the complex numbers in the standard way, by putting the real part on the horizontal axis, the imaginary part on the vertical axis, and we then plot the vectors in the standard way, the two things turn out to be very much the same. If I add the complex numbers, R happily does this with a plus sign, and plot the result, I get exactly the same result that I get when I add the two vectors. Furthermore, what's called the modulus of the complex number, calculated by the function capital MOD, agrees with our good friend norm that gives the length of the vector. You can see the same result down in the bottom. What's called the argument of a complex number is its angle above the x-axis in this plot. That's exactly the same as the angle between the corresponding vector and the first standard basis vector. So far, so good. When we're adding things, complex numbers and vectors seem to work exactly the same way. But multiplying complex numbers is a strange operation. It doesn't correspond to anything obvious we can do with vectors. If I multiply Z1 by Z2, I get 5 plus 5i. And the rule, which you may have learned in high school, is that the moduli of the complex numbers get multiplied, the modulus of the product and the product of the moduli are both 7.07, and the arguments, the angle with the horizontal axis, get added. They're both equal to 0.78. So how can we match up complex numbers with ideas in linear algebra? Well, the remarkable result is we can represent complex numbers by 2 by 2 matrices in the simplest imaginable way. If we've got a complex number that's x plus iy, we just put the x's on the main diagonal and the y's on the off diagonal to create what's called a conformal matrix. You can look at the bottom to see what the conformal matrix M43, which represents a complex number with real part 4, imaginary part 3, looks like. It's got 4's down the main diagonal, a minus 3 in the upper right-hand corner, a plus 3 in the lower left-hand corner. And you say to yourself, this looks awfully much like a rotation matrix, but the determinant isn't 1. The column isn't unit vectors. Let's see what we can make of this in terms of linear transformations. So we'll set up a nice looking plot, and we will see what happens to the first basis vector. There's the first standard basis vector, and here's the first column of the matrix. What happens to it? It got rotated, but it also got stretched. It was rotated through 37 degrees, but the length got multiplied by 5. And exactly the same thing happened to the second standard basis vector. So now we can make matrices for our two complex numbers. We have this convenient function for making a conformal matrix from the complex numbers 3 plus I and 2 plus I. And there are the two matrices. Notice they're both symmetric. Sorry, I said that wrong. They're both antisymmetric. Same numbers down the diagonal, but the numbers off the diagonal are opposite. If we add them, the resulting matrix is the same as the matrix for the sum of the two complex numbers. But now we can multiply them and get the same matrix. So let's do this two ways. First thing we'll do is make a conformal matrix from the real and imaginary part of the product of the two complex numbers. The second thing we'll do is multiply together the matrices that represent these two complex numbers. Behold, we get exactly the same answer. What's more, remember that in general, matrix multiplication is not commutative, but in this case, we get the same answer no matter what order we use for the two matrices. If you look above, you'll see that I multiplied the two matrices mz1 and mz2 and in two different orders, and I got the same answer. In fact, this is the one non-trivial case where matrices actually form a field. So I've made a complex number out of real part 4 and imaginary part 3. The hardest axiom to satisfy for a field is that the inverse of every non-zero element is also in the field. I can ask R to calculate the inverse of the complex number z. I can also ask R to multiply the modulus of z by the modulus of the inverse number. The answer is 1. Now let's try the same thing with matrices. We convert the complex number z into a conformal matrix. Same matrix. And we use the solve function to find its inverse. Same inverse. The first column, in fact, of this inverse matrix is the inverse of the complex numbers. So there you have it. Complex numbers behave exactly like these conformal 2x2 matrices. This is going to bail us out when we try to solve certain differential equations that are very important in physics, where complex numbers naturally arise, but because we're doing physics, we know that everything in question is actually a real number. Here's the curious mathematical fact that goes along with this. If you're looking for matrices bigger than 1 by 1 matrices, and you are excluding the rather trivial case where the matrices are multiples of the identity matrix, the only way you can get a set of matrices that satisfy all the axioms for a field is by using these conformal matrices. The technical name for this is isomorphism. These 2 by 2 conformal matrices correspond precisely to complex numbers in a way so that addition and multiplication on the two sorts of mathematical objects produce corresponding results.